Hey everyone, thank you so much for joining us today. We'll get started in just a moment. We're going to give folks a little bit longer to log on. Thank you.
Hello? Can you hear me?
Hi, Jaywin. Yep, we can hear you. We're going to get started right now.
Oh, okay. Thank you.
All right. Thank you all for joining us for the virtual firmware for Intel Trust Domain Extensions hosted by the UEFI Forum. I did want to take a moment here to introduce our presenter today. We have Jaywin Yao, who is the principal engineer at Intel. And I'm going to pass it off to Jaywin to go ahead and get started. Thank you.
Okay, thank you, Megan. So first, thank you everyone to join today's UEFI webinar. This is Jaywin Yao. I'm principal engineer in Intel. Today, I will introduce virtual firmware for Intel Trust Domain Extension technology. Here's today's agenda. I will have a brief introduction for Intel TDX. Then I will cover detail of the TDX Virtual Firmware, so known as TDVF. Then a lightweight TDVF, Shim. And finally, I will introduce a disk encryption use case for TD. So first, let me see why we need Intel TDX. Today, we have a hypervisor emulating a virtual platform. the hypervisor has the highest privilege, but a malicious hypervisor may tamper a virtual machine. So a customer may rent a VM from a cloud service provider. Then the VM may contain the sensitive data, such as some confidential information. The customer does not want the CSP know the sensitive data at runtime, and they hope the VM run in a confidential computing environment. So Intel TDX introduced an architecture element to help deploy the hardware isolated virtual machine, which is called a trust domain. With the protection of TDX hardware, the hypervisor can no longer access the data inside of trust domain. The TD is a hardware-based confidential computing environment. If you know Intel SGX software guard extension, the TDX is very similar with SGX on one hand. Both of them provide the confidential computing environment. On the other hand, TDX is a little different with SGX because SGX only supports to put the Ring 3 application code into a secure enclave. The application porting is required if we want to put a user-level application to a SGX enclave. In contrast, the TDX is to put the whole virtual machine into a secure environment. In that case, OS porting is required to enable TDX, but a user-level application can run as is. In brief, you can treat the TDX is to extend SGX from Ring 3 to Ring 0 with a TD enlightened hypervisor. Intel TDX is designed to isolate VMs from the virtual machine manager and any other non-TD software on the platform. It can protect the TDs from a broad range of software. On the left-hand side, the red box shows the legacy VMs. This is a traditional VM hypervisor environment, and the hypervisor has the highest privilege. It can access or modify the VM environment. On the left-hand side, the green box shows a TDX Enlightened OS inside of a TD. With the help of TDX hardware and a special Intel TDX module, the TDs are isolated from the VMM on the other TDs. Inside of one TD, the memory and the CPU state confidentiality in the integrity is provided to keep the sensitive IP or workload data secure from the most software-based attacks. Then the TDX uses MKTME for memory encryption. It can also augment some hardware attacks, such as offline DRAM analysis or DRAM interface hijack. TDX still needs the VMM to be the resource manager, so the denial of service tag is out of scope of TDX. So here is the TDX component. First, we need a TDX CPU hardware, then Intel TDX module, and this is an Intel signed software module. It runs in a special mode named Shim. Shim stands for Secure Arbitration Mode. The TDX module sits in a Shim protected memory. It provides the Shim core service to VMM and the TD core service to a TD. And the Intel TDX module manages the transition between a VMM and a TD. That means if a VMM wants to VM entry, it runs into the Shim. Shim switch the contacts and resume to a TD. While a TD wants to exit, so first it exits to a Shim, then Shim saves the TD contacts, then switch to a VMM. The Intel TDX module can only be loaded by a Shim loader ACM. The Shim loader ACM is signed and checked by the CPU hardware when it is launched. Then this Shim loader ACM will check the hardware configuration to see if it can meet the TDX launch requirement and load the Intel TDX module into the Shim protected memory. The last piece is a TD quote enclave. This quote enclave is also launched during system boot, and it is needed to provide the remote attestation for TD. So in TDX solution, only hardware TDX module, SIM loader ACM, and the quote enclave are in a PCB. So the VMM is outside of the PCB. Here is a system boot flow. For a TDX aware the platform BIOS must initialize the system for TDX. For example, the platform BIOS need to allocate a SIM protective memory with a SIM range register. Platform BIOS may launch a SIM loader to put the TDX module into SIM mode. Then the platform BIOS may pass control to the hypervisor or VMM. As alternative, the SIM loader ACM can also be launched by VMM if it is aware of it. Once the Intel TDX module is inside of the SIM memory, then the VMM can prepare the memory for a TD and use a SIM core to launch the TD. And the TDX module can do VM enter into a TD. Once there's a VM exit event from the TD switch to the TDX module. The TDX module can return back to the VMM. So the TDX module is between the VMM and the TD to prevent them tamper each other. So a normal virtual machine environment includes a virtual BIOS. For example, the EDK2 OVMF is an open virtual machine firmware to provide the UEFI service to a UEFI guest OS. The virtual BIOS is also required for a trust domain. We call it trust domain virtual firmware, which is TDVF. The TDVF owns the first instruction of a TD domain at the reset vector. It provides the UEFI services to a TD operating system. It also has built the chain of trust from the Intel TDX module to a TD OS. Current version of TDVF is based upon EDK2 Open Virtual Machine Firmware, OVMF, but the TDVF is a simplified one. It skips the PAI phase, and the memory discovered in SEC, and the SEC builds a hop and jump to the DXE directly. The key difference between the TDVF and the OVMF is the threat model. In OVMF, it is a normal VMM environment where the hypervisor has the highest privilege, so OVMF can trust the input from the hypervisor. But the TDVF is used in a confidential computing environment. The hypervisor is treated as a threat. The TDVF must not trust any input from the hypervisor because the hypervisor might be malicious. The TDVF must also validate the hypervisor input before use, and the TDVF must always measure the configuration input from the hypervisor and extend that to a measurement register. Those data will be used for remote attestation. Here is a picture of the high-level boot flow of a TDVF. The black color means the flow is very similar to existing OVMF. The orange one means the flow exists in OVMF, but it is updated in the TDVF. And the red color means the flow does not exist in OVMF and it is new in a TDVF. First, the reset vector in TDVF is different. The traditional OVMF has a 16-bit real mode entry point. The entry point in a TDVF is 32-bit protected mode. So then the VMM can pass a TD parameter we call a TD hop in a RCX or R8 register as a CPU init state. The TD hub contains any information that the VMM want to pass to a TD dynamically. For example, the guest physical memory location, the MMIO, etc. After the TDVF switch from the protected mode to 60-bit long mode, it passes the TD hub header to get the size. Because the TD hub is external input, the TDVF must measure the entire hub to a TD runtime measurement register to support the trusted boot. Once the TDVF gets the memory location from the TD hub, then the TDVF sec phase can initialize the private memory. And then it can prepare the PI DXE hub, locate the DXE core, and jumps to the DXE core. In DXE phase, the TDVF does the regular DXE initialization. For example, it initializes the memory management, the CPU multiprocessor, and the UEFI variable. It enables the UEFI secure boot to verify the third-party code, such as OS loader. It enables the trusted boot to extend the firmware configuration and any third-party code into TD runtime measurement register. TDVF will prepare the required ACPI table for the guest operating system. If the SEC does not initialize all memory, the rest memory will be initialized in DXE phase. Because the default memory in TD is encrypted, it cannot be used as a virtual device DMA. To support the virtual device access, the TDVF has a special IOMNU driver to switch the private encrypted memory to a shared memory for DMA access. After all DXE driver dispatched, the TDVF enters the BDS phase. It will enumerate all the volatile device, start the console, start the storage, then it load OS kernel and boot to the operating system, which is similar to a normal OVMF. The TDVF binary is similar to OVMF2. It's constructed with a UEFI PI firmware volume. We put all UEFI drivers into a boot firmware volume, the UEFI variable configuration into a configuration firmware volume. Inside of the boot firmware volume, there's a TD descriptor metadata. The descriptor metadata is located at the 4 GB minus 20H. It has a metadata offset. This metadata is used to describe the binary layout of the TDVF bin, such as where is the boot code, or where is the configuration, where is the temporary memory, and where is the TD hub could be. Those information will be passed by the VMM when VMM create a TD and load the corresponding data to a TD. The configuration firmware volume holds the provisioned UEFI variable, for example, the PK, KK, DB, or DBX, which will be used for the UEFI secure boot. TD starts from the protected mode reset vector. The address is same as the traditional one, it's 7F plus 0. The initial state of the general purpose register has some special meaning. For example, the IBX holds the guest physical address width, GPAW. It could be 48-bit or 52-bit. If the GPAW is 48-bit, then the guest should use 4-level paging. While the GPAW is 52-bit, then the guest should use 5-level paging. And also RCX or R8 hold a pointer of TD hub. The hub contains the TD information such as memory, location, and MMIO and IO information. And the RSI hold the virtual CPU index from 0 to n-1. This is support a multiprocessor launch. The multi-CPU supporting TDX is totally different with the traditional one. In traditional mode, only BSP is launched to reset vector, while all APs are in wait for CP state. The BSP needs to send the init CP sequence to wake up APs. However, in TDX, the all CPU jumps to the reset vector simultaneously by the Intel TDX module. The TDX module can guarantee that the virtual CPU index is from 0 to n-1, where the n is the total CPU. The TDVF will treat the CPU index 0 as BSP and treat the rest one to be AP. When the BSP boot the set code, while all APs are parked in a special location and wait to be woken up by the BSP. So we will discuss that later. In TD, you can use a TD core. So the TD core is a special hypercore to the Intel TDX module. It can only be initialized by the guest TD. So first, the TD core, VM core, is a way to invoke the VMM services. We will discuss that in next page. Second, TD core VP info is to get the TD information. For example, the GPAW is returned in RCX and the vCPU number is returned in R8. The third, RTMR extend, is to extend the TD runtime measurement register, RTMR. The RTMR is very similar to the TPM PCR register. Next one is the .VE get. Whenever the TD access some unexpected MMIO or memory information, it may get a virtual exception. So this VE info .get is to get the virtual exception information. It returns the exit reason and instruction information. Next one is MR report. This TD core is to return a TD report. TD report is include the measurement of the TD and TD configuration and the measurement of the Intel TDX module. The last one is a page accept. This is to accept a pending private page. TDVF will use this one to accept the unaccepted memory, which is locked by the VMM. TD core, TD VM core is introduced to let the TD invoke the VMM services. The first one is the TD VM core info. This is to enumerate all the VM core capabilities. The second one, map GPA, is to request VMM map a guest physical address to a private page or a shared page. The next, get code, is to request a code enclave to sign a TD report to a TD code for remote attestation. There are a set of instruction-related VM calls, such as instruction.cpuid, .hot, .io, .readMSR, writeMSR. Those are to request the VMM emulate those instructions. And you can see from the special TDVM call request MMIO. This is to request VMM emulate the MMIO access. The memory management is one of the most complicated part in the TDVF because of the new concept. In traditional VM, we only have the physical memory and MMIO. In a TD, there are 3 different types of physical memory. That is private memory, shared memory, and unaccepted memory. So first, the default physical memory type in a TD is a private memory. It means this memory is encrypted by the TD specific key. The VMM can use a Shim call page add to add a memory page for the TD. Then the TD can access this private memory directly. The VMM cannot access this TD private memory. The private memory can be switched to a shared page. A shared page is a memory that can be accessed by hypervisor. It may be used for communication or virtual device DMA. The shared page setup is same as private. The only difference is that they need a shared bit in the page table entry. The shared bit, also known as S bit, if this shared bit is cleared for the private memory, and the shared bit is set for the shared memory. A TD can switch the private memory to a shared memory or switch the shared memory back to a private memory. Use a TDVM called map GPA. The third one, unaccepted memory, is a new concept. It means a private memory is declared by the VMM, but it is not accepted by TD yet. The unaccepted memory is added by the VMM via a Shim call page arc. Then the TD must use a TD call page accept to change the unaccepted memory to a private memory, then start to use it. The unaccepted memory cannot be accessed directly before it is converted to a private memory. The last type is MMIO emulated by VMF. The MMIO cannot be accessed by the TD directly like a physical memory. The TD must use TD call or request MMIO to access that. If the TD access the MMIO directly, upon the VE will be triggered, and we may use VM call to access MMIO in this .ve handler. And here is a summary of the four memory types. We have introduced private memory, shared memory, unaccepted memory, and VM and emulated MMIO. So for all those memory, the type can be changed. First, the unaccepted memory can be changed to a private memory. This is to support the lazy memory in it, because the adding of TD private memory is very time consuming. The VMM can choose to add a small amount of private memory by default and declare the rest uninitialized memory to be unaccepted. Then the TDVF or OS can use a TD call to accept those unaccepted memory to support lazy memory initialization. And the private memory to shared memory switch is to support communication and virtual device DMA, and we have introduced that in the previous page. And here's a figure of the memory state transition during boot. First, the VMM add a minimum private memory to a TD, include TD hop, TDVF code, and a small amount of memory for stack or heap. Second, TDVF may set up more private memory and continue to run the whole system into the UEFI environment. Third, the TDVF may choose to initialize all TD private memory. This step is optional, and it may be left to the operating system. Step 4, if a virtual device requires a DMA buffer, then the TDVF can convert some of the private memory to a shared memory for the communication. After the DMA buffer is used, the TDVF can convert the shared memory back to the private memory. All those memories for all those four memory types exist in different phases. The private memory is the default one. There's no need to indicate that in UEFI memory map or PI GCD entry. The shared memory is the same as the default private memory. There's no special indicator other than the page table shared bit. And we don't need to distinguish the private memory and the shared memory in UEFI memory map because all shared memory should be converted back to the private memory at the exit boot service event. We may need an indicator in the PI hub to distinguish with the private memory and the public memory. Then we may use a resource attribute encrypted here. The third, unaccepted memory is a special one. The TDVF need to report the unaccepted memory to OS because TDVF might not convert all unaccepted memory to private. Then this work is left to the operating system. A new UEFI memory type, unaccepted memory, is defined as an indicator, similar one in GCD, PI hub, and ACPI E820. The MMIO doesn't need to be reported in UEFI memory map because all MMIO are emulated, and we assume there's no runtime access is required. The emulated MMIO may be reported in ACPI ASL. The ACPI table in TDVF is similar to the one in OVMF. All CPUs are reported via MATT ACPI table. However, since TD cannot use any specific sequence to wake up AP, we define something new. A new multiprocessor wake-up structure in MATT is defined to describe a 4K byte mailbox. The TDVF allocate the mailbox structure and report the mailbox to operating system. At the same time, all APs loop to check the wake-up vector in the mailbox. After OS fills the AP wake-up vector APIC ID and update the wake-up and send the wake-up command. Then each AP will check the command APIC ID and jump to the AP wake-up vector if there's ACPI APIC ID matches. A platform BIOS or even a virtual BIOS may support TCG trusted boot. Comparing with TCG, the concept of a TD trusted boot flow is similar, but the implementation is a little different. The TDX supports the measurement and the remote attestation, similar to TPM-based static root of trust for measurement. The TDX boot flow extends the boot component into a set of measurement register. Different with TCG, where the TPM defines 8 PCR registers for firmware boot. In TDX, we have two types of measurement register. First, the when VMM constructs a TD, the VMM uses a theme called MR extend to measure the whole TDVF in the private memory into a TDMR. That is a TD measurement register. Second, after a TD launch, the TDVM may use a TD called RTMR extend to measure the additional TD private memory into runtime measurement register. This includes the configuration firmware volume or the TD hub, which is passed from the VMM. You can see this figure shows the measurement in a summary. The VMM load and measure the TDVF boot firmware volume in TDMR, and the TDVF measure config FV and the TD hub into RTMR is 0. Then the TDVF measure the OS loader and disk partition into RTMR 1. And once there's a remote entity want to attest the platform, it can get a TD report. The TD report include the RTMR register and include one TDMR register and 4 RTMR register. This table is a comparison between the TCG measured boot and the TCG measurement and TD measurement. So first, the firmware code goes to RTMR. The firmware code goes to the TDMR, is done by VMM. Firmware data or configuration goes to the RTMR, such as config FV or TD-hub. Then the secure boot configuration, also a configuration, goes to the RTMR 0. The boot-related code or data goes to RTMR 1, such as OS loader or code or disk partition. Inside of the TDOS, the OS kernel may extend the application to RTMR 2. The RTMR 3 should be reserved for some special usage. The TD trusted boot interface is the one is very similar to the TCG interface. The TD defines the TCG2 protocol and the TPM2 ACPI table to pass the event log, where the TDVF uses the UEFI TD protocol to provide the measurement service and let the OS loader extend to RTMR. And the TDER ACPI table holds the whole TD event log address and size. Platform BIOS may support UEFI secure boot is same thing. TDVF can also support UEFI secure boot. The virtual BIOS may verify the OS loader or kernel user key provisioned in UEFI variable. The only difference is that inside of TDVF we don't support persistent storage, so all the OS variable are volatile. So we require all the PK, KEK, DB, DBX be provisioned at TD build time. And of course, this key will be extended to TD RTMR register. Here we want to summarize the TDVF design principle because TDVF is the foundation of the trust domain. Vulnerability in TDVF may impact the whole channel trust. The golden rule is to keep it simple. We should remove the unnecessary feature such as the PI phase, and we don't want to expose the unrequired external interface such as a whole full TCP/IP network stack. Second, we should apply the best practice to validate all the input before use, such as hub configuration information from DMM, and don't trust any input from DMM. The TDVF must build the chain of trust. It should measure all the configuration input before use. It should not use a mutable non-volatile storage because it may change the MR register. Also, the internal non-volatile storage may be modified by the EMM. So we have introduced a full TDVF which provides the UEFI service to TDOS. However, in the virtualization environment, not all OS requires UEFI, such as some special container case. The container may just need a lightweight virtual firmware, such as a cloud and hypervisor firmware. Also, the container may depend on non-standard UEFI interface. We might have a small service TD which provides a use case specific services in a standalone TD environment. The service TD might run in a bare metal environment. In order to support those special use cases, we introduce a TD Shim concept. The TD Shim is a tiny TDVF. It only includes a SEC, initial program loader, and it does not have the UEFI core. Instead of boot to a UEFI core, the SEC IPL can boot to any payload. It could be UEFI, it could be a container OS, it could be a Linux payload, or even a Zephyr RTOS. The TD Shim does not include any device driver. It may include some static ACPI table if it can use. It may DTMP Wakeup structure. If the TD Shim does not have ACPI table, then it can use some other way to report such information. So, for example, the NP table extension. Because the TD Shim does not produce UEFI memory map, it can just use the E820 table to report the memory location, include the unaccepted memory. This figure shows the TD Shim boot flow. The reset vector park the AP, then switch to long mode and set up stack for C code, then jump to the IPL. The IPL code matches the TD hub, pass the TD hub to get the memory info and accept the private memory. Then it load the payload and jump to the payload. And we do some prototype for this TD Shim. We show a small reset vector could be a 32K, include a fixed page table, whereas 24K. And the small IPL could be 25K. It includes including the SHA-384 hash algorithm to measure the next boot component. Besides that, next I will introduce a special use case that for TD disk encryption support. Today, VMM may either get a storage volume key and decrypt a VM disk because VMM has the highest privilege. The VMM can get the key and do the decryption. In TDX, VMM is not trusted. As such, the TD must get the storage key by itself and decrypt the VM disk, and we do not allow VMM to see any information about the key. So this picture shows a high-level component layout on how we support the disk encryption solution. So first, we need a special key agent driver to inside of the TD. It can talk to a remote key server. And this key agent driver can get the storage volume key from the key server and pass the key information to OS loader or OS kernel. Then OS loader or kernel can decrypt the disk and load the data from the disk. The key agent driver could be a special driver in TDVF, or it could be integrated in OS loader or OS kernel or even OS device driver based upon the use case. To support that, case, the storage volume key is a secret, so we must maintain the confidentiality of the key. Only TD and the key server should know the key, and the VMM should not know this key. To support the secure communication, we use a network TLS protocol. We can use this protocol to maintain the confidentiality of the integrity of the communication. The TD and the key server should also authenticate each other to resist the man-in-the-middle attack. So first, the key agent worked as a TLS client. It can use a server certificate verification to authenticate the key server. The server certificate can be provisioned into a UEFI variable built at build time deployed in the UEFI variable solution. This is quite similar to UEFI HTTPS boot. Second, the server can use the TD remote attestation flow to verify a TD. Well, we can introduce in next page. This shows a very simplified TD attestation flow with a code enclave support. So first, when a code enclave launches, it generates a coding key. Then the code enclave can talk to a provision certificate enclave PCE and let the PCE sign the quoting key. When a TD launch, it can get a TD report from the CPU hardware, and the TD report include the TDMR and the RTMR information, as well as the TDX module and secure version number, etc. CPU will generate a MAC for the TD report. However, the TD report can only be verified on a local machine with E-verify report instruction. It cannot be used for remote attestation. In order to support that, the TD must pass the TD report to a court enclave and let the court enclave change the TD report into a TD code. That is step 2. Step 3, the court enclave calls the E-verify report instruction to verify the TD report and make sure the report is correct. Then it will sign the report with its quoting key. Then it returns the TD quote to a TD environment. Step 5, the TD can pass the TD code to any third part for remote attestation to verify. Then the third part can get the PCE public key from Intel website, verify the quoting key, then use the quoting key to verify the TD code. Then it can check the TDMR register and the RTMR register expected. Then the key server may use this way to verify TD client who requests the disk encryption key. Once the key server verifies the TD, the key server can pass the key to a key agent. Then the agent puts the key into a storage volume key location ACPI table. Then or the OS loader or the kernel can get the information from the ACPI. The key agent location could be use case specific, TDVF or OS. If it is in OS, then the TDVF can be simple. If in the TDVF, then we can have a common operating system. So we have pros and cons. The last page, I would like to summarize today's talk. So we described the Intel TDX. It supports the memory and the CPU state confidentiality and integrity. It supports the measurement and the remote attestation. We introduced the TDVF. The TDVF support the trust chain. It is to support trust boot. It builds a chain of trust for TD and launch a TD Enlightened OS. TD Shim is a tiny TDVF, can boot to any special payload. Then we introduced the TD-based disk encryption use case. The key agent get the disk encryption key from a remote key server, and after TD attestation, the key agent can be in TDVF or OS loader. Then the OS loader kernel can get the key from agent and decrypt the disk. And here I list some of the reference. We published the TDX specification, and the white paper include the virtual firmware design guide against the hypervisor communication interface. And we also open source the POC code on the EDK2 staging tree, include the TDVF package and the TD Shim package. With that, would like to see if there's any questions for today's talk.
Thank you, Jaewon. All right, everybody, we're open for questions now, so please feel free to submit those via the chat box. After we wrap up here, we will also move over to a WebEx where there'll be a live interactive discussion with Jaewon as well. We'll give it a minute for folks to submit questions. If we don't receive any, then we can move over to the WebEx. All right, first question. What tech besides SGX do you see this replacing? Maybe T-boot?
T-boot is not related to either SGX or TDX. So T-boot is a dynamic root of trust measurement solution, support DRTM. It uses the TXT. The way for T-boot work is we boot a measured hypervisor, and that's it. But for the TDX, it means you do not want to trust the hypervisor. You just boot a TD trust domain to support the confidential computing environment. I would say this T-boot is not related here. So which tech besides SGX? Sorry, I see too many. See this replacing. So for SGX, so I would say TDX is the replacement of SGX, but the TDX can be coexist with the T-boot. Those are using different use case.
Great. Next question. Is TDX able to mitigate side channel attacks?
Side channel attack? No, I don't think so. You still need do some protection to follow the side channel guideline for that. It is same as the SGX. We need to follow the side channel development guideline. So TDX not serves that purpose, I believe. If you want to expose some information, the information will be exposed.
Next question, are there any plans to support non-volatile UEFI variables?
Non-volatile UEFI variable, I don't think so at this moment, because the TD cannot maintain any non-volatile storage. So if the non-volatile storage is emulated by the VMM, then the VMM may modify that. At least today, we don't have plan to do that, I would say. So the downside is that the UEFI, so all the UEFI variable must be provisioned when you build a TD.
The next question is, can I develop my own TDX ACM that's signed with my own keys?
Can I develop my own TDX signed with my own keys? I think in the first generation probably not. It's not supported, but I do see some discussion around that if we allow the customer to sign with their own key. So short answer, no, but we'll consider that unless there's some special use case.
Great. What kind of OS can work in this trusted domain without modification?
I would say OS is required to modify. So here, the benefit is that the user level application might not need to be modified. As things is touch the system resource, I believe it need to be modified. For example, the OS may need to call some CPU ID instruction. Then you need to use a special VM call, TDVM call, to access that. You can maybe OS need to call read MSR, write MSR. OS need to access MMIO region. All those actions need to be changed by using some TDVM call.
Is this all going to be open source? If not, what parts are proprietary?
It is all going to be, I would say TDVF will be open source. The Shim loader and TDX module is not open source yet. It is Intel developing the software and signed by the Intel key. But all the TD, the component in TD will be open source, like TDVF or TD Shim. I would say they are open sourced.
What are the plans for changing the POC to real production code?
Okay, sure. Yes, currently this is a POC code. We will actively working on that and make it. Eventually, we plan to integrate that into the EDK2 master when the TDX hardware is launched, which will happen in next year, Q3 or Q4, I would say.
Great. On that note, we are going to move over to the live WebEx discussion now. That should be displayed on your screen, the link to that, as well as in the presenter to audience announcements section. Jay, when I also put the code in the presenter to presenter chat for you to join as well. So thank you all so much for joining us today. And we look forward to continuing this discussion on the WebEx in a moment or two. So we'll talk to you all in a few minutes. Thank you.
Okay, thank you, Becca.